Again, what can x not be? Well, x cannot be negative 8. So that's going to be my vertical asymptote, unless something cancels. Now, that numerator, I don't know if I can factor it. I think I can factor it. It'll be x plus x minus a positive times a negative equals a negative. And I think 8 times 6 is going to do it. So on second thought, I don't think I have a vertical asymptote. Remember from chapter 1, so again, I'm rewriting g of x as y. If this cancels out, which it does, that means that the graph is going to behave like a line. This one's going to be weird. It's actually going to look like the line, when you simplify this thing, you only have x minus 6 left over, which means it's going to be a line that crosses negative 6 with a slope of 1. This is the graph, the way it's going to look. However, at the very beginning, I knew that x could not be negative 8. So this time, at negative 8, and I'm not going to make this to scale, but let's say this is negative 8. At negative 8, at negative 8, there's going to be a tiny, tiny, tiny little hole. There's going to be a hole in the graph. So the domain here would be, if I asked you for the domain, it would be from negative infinity to negative 8, and then in union with negative 8 to infinity, meaning that the graph passes through all the points except negative 8. The range would be, if you put a negative 8 there, right there at negative 8, where would it be? So the range would be from negative infinity up to that number, and that number to infinity. Again, because of lack of time, and in class we can go and analyze it a little more carefully, but I wanted to show you that that actually looks like a straight line. Okay, if you graph it, that's going to look like a straight line. All right. I'm going to move on to the next things. Again, some of the other stuff we can talk about in class. We continue analyzing graphs as we move on. Again, just to show you the different type of graphs that you're going to get. Here it says graph and determine the domain and the asymptote. So once again, if you look at this function, we're looking at a now, notice that nothing cancels out. You know how the other one, the x plus 8, canceled out? So that actually became a hole in the graph, and we've done that. That would be point discontinuity. That's from chapter 1. Well, this one, nothing cancels out. So if nothing cancels out, that means that x cannot be negative 4, and x cannot be 5. That could be your domain, by the way. Remember, the domain, you can write it in interval notation or set notation. If you write it in set notation, you would say that the domain is the values of x such that x cannot be negative 4 or positive 5. Remember, we were doing the x belongs to the element of all real numbers, meaning x can be all the other real numbers except those two. So you can write your domain like that in a set builder notation. If you write it the other way, you would say that it's from negative infinity to negative 4 in union with negative 4 to 5 in union with 5 to infinity. And that basically says the same thing, that it can be any number that's negative infinity all the way up to negative 4, then it stops. Then after negative 4, it continues until 5, then it stops. Then after 5, it continues to infinity. So you can write it either one of these two. You will be responsible for writing the domain in either notation. Remember that the assignments are in multiple choice. Your tests sometimes are multiple choice, sometimes they are in free response. So just be able to answer that. So that's how you answer the domain. You basically look at the denominator. What can x not be? And that's you're basically determining your domain, what x can or cannot be. Asymptotes. Okay. If I worked it out, now I'm not going to work it out, but if I did the FOIL method, I would get x squared. Well, I could do it. X squared, if I did it, I would get x squared minus x minus 6 if I do the FOIL method. And in the bottom, I would get x squared minus x minus 20. So again, I know for a fact that the graph of this thing is not going to exist at negative 4. So let's say over here somewhere. And x equals positive 5 is not going to exist. Those are my vertical asymptotes there. And then for my horizontal asymptotes, well, it's a y equal to. How many times is x squared going to x squared? X squared goes into x squared once. So at x equals to 1, somewhere around here, okay, there is a horizontal asymptote. So the graph is guided by that goalpost looking thing. Now I went ahead and graphed it for you. Let me make sure I find it here. If it's not this one, it's the next one. Oops, maybe I didn't. Oh no, maybe I did not graph it for you guys. If I did not, then I'll go back and graph it for you. Let's see, let me double check one more time. we have, oh, there it is. Isn't it that one? Let's see, x plus 2x minus 3. Yeah, there it is, right there. Okay, so there's a vertical asymptote here at x equals -4, at x equals +5, there's another one, and at y equals 1, there's your other. So it looks like we're going to the extremes here, and in the middle, you got an upside-down parabola-looking shape. So the graph looks like something like this, and like that, being guided by those horizontal and vertical asymptotes. So again, if I ask you for the asymptotes, you would say my vertical asymptotes are x equals -4 and x equals 5. And then the horizontal asymptote is going to be 1. It's going to be y equals to 1 right there. So that's how you're going to do those right there. You're going to look at the denominator and then analyze it. And then that's how you're going to determine your domain. And then, of course, you're also going to use them to determine your horizontal and your vertical asymptotes. Okay, we can do the same for the next one. Again, guys, look at, now this is a, let me see, this one, the next one, letter B, is now a quadratic in the denominator. So if you factor that out, you're going to get x plus, and looks like, ooh, wait a minute, I can't factor that one. That's not factorable. So that means if it's not factorable, you will not be able to find the asymptotes. As a matter of fact, I went ahead and did it. Now I used the quadratic formula here in the bottom. The x equals -b plus or minus square root b squared minus 4ac all over 2a. I used that to figure out what kind of answer I would get, and I got a negative inside the square root, which means that the only way that could be 0 in the bottom is with an imaginary number, which does not exist. So in other words, this graph will exist throughout the life cycle of the function. Now this is a weird case where the domain is actually from -infinity to +infinity, and the range as well. But what I'm going to ask you to do here is something different. What kind of asymptote do you get as far as the horizontal? So there is no vertical asymptote because I can't factor the denominator and I can't solve it for any line that will make the graph disappear. And again, we'll talk more about that in class. But for the horizontal asymptote, which is your y equal to, take a look at this. How many times does x squared go into x? Well, it doesn't. It's too big. It goes in 0 times. So that is my horizontal asymptote there. If I graph it, and I think I already prepared it for you. Let's make sure here. Yep, here it is. Now it looks, now I zoomed in all the way in the bottom just to make sure, and you can go into Desmos. And that graph, a lot of times when that graph goes like this, you have a vertical asymptote and the graph kind of gets closer and never touches. But this one, if you look at it, it actually does connect. So it does connect there at the bottom and go this way. And then on the right side, I believe it goes above and then below, and then it tries to get back to 0 and doesn't. So y equals to 0 is your horizontal asymptote. That's the only thing we have in this graph is a horizontal asymptote of y equals to 0. It doesn't have a vertical asymptote, and that's rare. A lot of these rational functions usually have, if anything, you'll have a vertical asymptote, and sometimes you don't have a horizontal asymptote. But you might have an oblique asymptote. All right, I just wanted to show you some of the weird graphs that you're going to get here. And again, right now, because of time constraints, I'm going to continue going. Note, for example, on letter C, right there, what can x not be? Well, x cannot be 0. So you're going to have a vertical asymptote at x equals 0. On letter D, you're going to factor that, and you're going to have 2 vertical asymptotes. So really quick, just to mention some things about these. The vertical asymptote for letter C is going to be x equals to 0 because x cannot be 0 because 0 squared is 0. The vertical asymptote for the next one, well, you would have to factor it. If you factor it, you get x plus 4 and x minus 3, which neither one cancels with the numerator. So there's going to be 2 vertical asymptotes at x equals -4 and at x equals +3. As far as horizontal asymptote is concerned, y equal to, right? How many times does x squared go into x on letter C? Well, it doesn't. X squared doesn't go in there. It's too big, all right? 0. For the horizontal asymptote here, how many times does x squared go into x cubed? Ooh, now we got something. If you actually divide that, you're going to get how many times does x squared go into 2x cubed? It goes in 2x. So actually, you're going to get not a horizontal asymptote, but what we call an oblique or a slanted asymptote. If you graph that one, you'll see, let me see if I still have it here. It's not that one, it's this one. See right here, the line y equals 2x is a line that's going to guide. So this part of the graph is actually going at an angle. It's going at an angle and it's following a slanted line, and that's why we call it a slanted asymptote or an oblique asymptote. Whenever the denominator, whenever you can divide it and you get a variable, you're going to get, if you get a variable, that means you get a line or a slanted asymptote. So that's a weird graph, and that's some of the things we're going to talk about in class. This one gets an oblique asymptote. We are at 27 minutes, so I'm going to get to the last part, which is solving equations. All right, for solving equations, guys, what you're going to do, your job is to leave x by itself, but we hate fractions, so what we try to do is we try to eliminate the fractions by multiplying by the least common denominator. Well, to get rid of 4 and 5, you're going to multiply by 20. Multiply both sides by 20. So if you multiply this side by 20, it's 20 times 3 is 60, 60x, divided by 4 is going to be 15x. You can also divide first, like 20. If you go 20 divided by 4, that's going to be 5, and then the 5 times the 3 is a 15. So if you want to divide first, you can. 20 divided by 5 here is going to be 4. 4 times 3 is 12. You can do it like that, or you can do 20 times 3 is 60. 60 divided by 5 is 12. And then over here, 20 times negative 6 is negative 120. Now we just go ahead and subtract 12 on both sides. That's 132. And then you divide by 15. So whatever this results in, let me see, 3, 4, 5. I think you can divide it, you can reduce it by 3. So if you reduce it by 3, you're going to get 5 here. You get negative, let me see, 44 fifths. I believe that's the answer right there, negative 44 fifths. You can double check my math. If not, when we get to class, again, we'll talk about it. We're very close to the end, guys. So letter B, the only fraction is that x there. So if I want to get rid of that x, I multiply it by x. So you're going to multiply by the denominator or by the least common denominator if you have more than one. By multiplying by x, what happens is you do mathematical magic. When you multiply by x in an expression that is dividing by x, well, the x are going to offset. They're going to cancel out. The only thing left is 8. See, we made the x disappear. But you have to do it to the entire side. So x times x is now x squared. And then 4 times x is 4x. Now you bring the x to the other side, the x squared to the other side. You have x squared plus 4x minus 8 is equal to 0. At this point, you can try to factor this out and solve it, and you get your two answers there. I think this one, if it's not factorable, then you're going to have to use the quadratic formula to solve it. But I wanted to take you there, because from there we can do it. All right, the last thing we're going to do is this letter C right here. On letter C, we're going to multiply by x minus 4 and by x as well, because I want to get rid of those two things. So I multiply by x minus 4 and by x. When I do it to that first term, the x minus 4 cancels, and the only thing left is the x that gets multiplied by 3. When I do it to the next term right here, the x cancels, and the only thing I get to multiply is the 2 with the x minus 4. So I get 2x minus 8. So that is on the left side. I'm sorry, this on the left side, this is on the right side. And then on the other side, when you do 1 times x minus 4 and x, you're going to have an x minus 4 and an x that neither one is going to cancel. So that's what you're going to have there. Okay, if we add these, you're going to have 5x minus 8. If we multiply these, I'm going to have x squared minus 4x. Now there's something you can do. Bring over everything to the other side. You're going to have x squared minus 9x plus 8 is equal to 0 because I took my 5x and my negative 8 to the other side. So x squared minus 9x plus 8. At that point, you can now factor it out and solve it. You're going to have x and x. See, once you have the quadratic, you can factor, you can use quadratic formula, the square root method, whatever you need to do to solve that quadratic. In this case, it's 8 times 1, right? Yeah, that's going to do it. So in this case, you're going to get x equals to 8 and x equals to 1.